Okay, everyone, let's do this question 1 from the June 2022 CSEC Physics Paper 2. So this question is about the activity of a radioactive substance, which was measured over a 6-minute period. So the results are recorded in this table 1 below. So if we look at table 1, we see that there's a time and there's a activity, or this in units of disintegrations per minute that's associated with that time, right? So we have our activity and the corresponding time at which that's the activity of the sample. And we go from 0 minutes to 6 minutes. And so we see that the activity is changing from 80 to around 4 over that time period, right? Of 6 minutes. So for part A, the question is asking us to use the grid provided in figure 1 on page 5 to plot a graph of activity versus time, right? So we're going to put our activity on the y-axis and time on the x-axis, right? Because it's versus time. And then we're supposed to draw a smooth curve through the points that we get. And this is all for 8 marks. So this is the graph that I came up with. So let's see here. Maybe let me zoom out a little bit. So let's see. Fit to one full page. Okay, so this is my graph that I got. So again, we're plotting activity on the y-axis and then time on the x-axis, right? And of course, our units for activity, disintegrations per minute, and then the time is in minutes. So I just kind of plotted all the points on the graph. They're like 6 points. So I plotted them with their corresponding time. So t is equal to 0 was 80. So that's my first point. And then this is my second point of 50 at 1 minute, and so on and so forth, right? And so for the scale, I just use a 2 centimeter scale to represent 1 minute, and then 2 centimeters to represent 10 disintegrations per second. And that way I found that it was fairly easy to plot the points that way, okay? So this is the curve that I drew, the smooth curve that I drew to my point through my points. And so let's go back up now to see what the rest of the question was asking us to do with that plot. So let's go back up. Okay, so before they ask us anything concerning the plot, so we did our plot and we're moving on to the questions now. So the first question, so B part I is asking to define the term half-life. So as we know, the half-life of a radioisotope is simply the time taken for the mass or the activity of a given sample of this radioisotope to decay to half of its value, right? So if I have 10 grams of a radioactive sample, the time that it takes for me to get to 5 grams, which would be half of that 10, is what we refer to as a half-life, okay? So this should be good for 2 marks. So this is my graph again that I'm showing here on this page, which is page 5. So let's move on to page 6 now. And page 6, on this page, they're asking us firstly to use our graph on page 5 to calculate the average half-life of the radioactive substance, the average half-life, right? So let's look back at our graph again on page 5. So half-life, right? Remember we said half-life is the time taken for either the activity or the mass to decrease to half of its initial value, right? So for this question, we started out with an activity of 80 disintegrations per minute. So I decided to choose 40, right? So 80 to 40, the time taken to go from 80 to 40 would be 1 half-life, right? So all I do here is I find 40 on my graph and I follow this line over to the curve and then follow that down to my x-axis. And when I do that, I come out with a time or a half-life of 1.6 minutes, right? So it takes me 1.6 minutes to go from 80 down to 40, right? And so that's my half-life of 1.6 minutes. I also chose a second point which would correspond to the activity going from 40 to 20, right? And so to go to 20, if I go to 20 and I come all the way across, right, then I end up at 3.2 minutes, right? And so to go from here at 1.6 minute where I'm at 40 to now over to 3.2 minutes where I'm at 20, that indicates that the half-life is simply 3.2 minus 1.6, so that's 1.6 again, right? So that's my half-life there, going from 40 to 20. Then finally, okay, so let's see. So our half-life then, I took the average of those two, right? So 1.6, 1.6. So my average half-life is the same, 1.6 minutes. Okay, and I got that from the graph as I just showed. So then for part 3 now, it's saying on your graph, use the dotted line to determine how long it would take for the activity of the sample to be reduced to 10 disintegrations per minute from the original activity level. So if we go back to our graph, we're starting at 80, and they're asking how long does it take to get down to 10, right? So all I do is I find 10 on my graph, and I follow that all the way over to my smooth curve, and then I follow that line down to my x-axis. And when I do that, I come out at 4.5 minutes, right? Roughly, based on my graph, I come out at 4.5 minutes. So what that means is from the time we start here at t is equal to 0, where we're at 80, it takes me 4.5 minutes to get down to 10, okay? So to get down to 10, it takes me 4.5 minutes total. So that, I put that on my answer sheet here on my line, and I say it takes me 4.5 minutes according to my graph to get down to 10 disintegrations from that 80 that we started with, okay? So 10 is here, I come across and I come down and I land at 4.5 minutes, okay? So that's our answer for this part, and that's worth 2 marks, so we're on our way. So for part C now, part I, we are supposed to define the term nuclear fission, right? So nuclear fission refers to the splitting of a large atomic nuclei. So we have a large atomic nucleus, and we're going to split that into 2 nearly equal parts, and that's going to result in a large output of energy and a decrease in mass. Okay, so fission, when we hear the word fission, that's splitting up, right? Fusion would be a joining of 2 things, 2 smaller nuclei, whereas fission is the splitting, right? It's a splitting of a large atomic nuclei into 2 nearly equal parts or smaller units, right? And when we do that splitting, we're going to release a large amount of energy and a decrease in mass. So this is all encompassing and should be solid for our 1 mark here that they're allotting for this definition, okay? So it's just a splitting. Make sure that you capture that. Fission means splitting, okay? So now we're moving down to part 2 of C, right? So part 2 of C. And so in part 2, they're given an equation as this equation as an example of a nuclear fission reaction, right? So we see that for this splitting, we are bombarding the nuclei of a uranium-235 isotope, and we're bombarding that with a neutron. And when we do that, we're going to split up the uranium-235 into a krypton, right? And a barium here, right? So we end up with these 2 smaller nuclei, and as a result of that, in that process, 2 neutrons are given off as well as energy, right? Remember, we said there's some energy given off as well. Okay. So now the rest of the question is asking us to use the atomic mass data for the nuclei given in this table to calculate the energy, right? So we have to find a delta E, the energy released in this reaction. So we are finding this energy pretty much, right? And we have to give our answers in joules. So that's important to note. They want us to give our answers in joules, so we have to make sure that our units align with that, okay? So this is table 2, and table 2 is showing us the nuclide and the corresponding atomic mass. And it's important to note that the atomic mass that they gave us is just in U, right? So atomic mass units. And so we'll have to convert that to kilogram. And so they give us the conversion factor here. And so I just went ahead and did that right away. Just multiplied my atomic mass units in AMU times what the kilogram equivalent is. So I did that for all of these to convert it to kilograms, because we need our answer in joules, so we can't work with these numbers, okay? So then I came down here and I'm just kind of explaining the steps that we have to take to answer these kinds of questions. And so the first thing I said is that to calculate the energy released in the reaction, which is what the question is asking us about, we have to use Einstein's equation of mass energy equivalence, right? And that equation just simply states that the delta E, or that energy release, is equal to delta M, so our change in mass or loss in mass or mass defect, times the square of the speed of light, right? So this is our key, this is our big equation that we have to be able to use to be able to come up with this energy released, right? So this is the first thing that we need to know, is that that's the equation that we're gonna have to use. So I just kind of jotted that down here, first thing. And then we need to first convert the atomic masses from the table to kilogram, and I did that here. And then we can calculate the change in mass for the reaction, okay? So those are the steps that we need to take first and foremost. So we did that. Let me undo that. Let me undo that again, so it's not muddled there. Okay. So we need to first convert the atomic masses from the table into kilograms. So I did that here, right? And then I just like rewrote the equation, the nuclear equation, right? And so I know what mass to put where. So effectively what we're finding first is the change in mass, delta M, which is corresponding to this energy that gets released. And so all I'm doing is plugging in my values that I got for the masses, the respective masses of the different species. So on the left-hand side, I have the uranium-235. Then I have the one for that 1 neutron. And then I have my krypton here. Then I have my barium here. And then I have my 2 neutrons here. And then, of course, my delta M, which is my unknown. And then, so I just do delta M is equal to this side, all of this, which is this, minus everything that was over here. And that gives me my delta M. And delta M comes out to be 6.3246 times 10 to negative 28 kilograms. And then finally, to find the energy again, now we're going to have to apply this Einstein equation, right? So then my delta E will be equal to delta M C squared. And I just calculated my delta M, so I'll just plug that in here, right? So that's 6.3246 times 10 to negative 28 kilograms times 3.0 times 10 to the 8 squared. That's C squared, okay? So then, finally, for my delta E, when I plug this in my calculator, I come out with a value of delta E of 5.6921 times 10 to the negative 11 joules, right? And because my units were good, I did my conversion of mass, and this was kilogram, right? And this was ended up being what? Meters per second, and that whole thing is squared, right? Then that whole unit ended up being what? Kilogram meter squared per second squared, and that whole thing, right? This whole thing is a joule. So my units worked out, okay? My units worked out well. So that's why I ended up with my joule being my unit of energy down here, okay? Now, one last thing I want to say about this is that I went through the effort of converting all of these individually to kilogram. What you could also do alternatively, you could just use the U as it's given to find the mass defect. So in U, so you'd find the mass defect in these U units, right? But once you find the mass defect, if you find the mass defect and everything is in U, then at that point now you can do the conversion to just multiply that value by this conversion factor, right? So that might save you some time instead of going through the painstaking effort of doing it one by one by one by one. What you might do is just use these values as they are. But remember now, once you get that mass defect, it's going to be in U. You have to convert it to kilogram and you just multiply that by this number, okay? And that should yield the same results as I got here, right? So that might save some time and some confusion, right? If you do it that way. But this way also works as well. So with that, if there are any comments on this and how we arrived at the final answer, definitely drop that below. If this video was helpful for you as well, drop that down below. And as usual, please like this video, subscribe to this channel, and I will see you in the next video.